All right. Good afternoon, everyone. It's Monday afternoon. You'll either see this Monday or Tuesday. Remember, I post the videos and I post the PowerPoints um, into the content. So all that stuff is there. Okay. So we left off the evolution of a sun-sized star, which we ended up using up the hydrogen, right? Core compresses, the helium core compresses, right? You get hydrogen burn, right? This intense burning around the shell causes the star to expand and cool, so it becomes a red giant. Okay, so that's kind of where we left off. You're going to need to be able to explain to me by the end of the week, right? I'm going to have you make a video, kind of like I'm doing, right? The software has a video record function where you're going to submit a video. Excuse me. You're going to submit a video explaining the evolution of the different size stars. Okay, the ones, all the different variables, right? The nothing. Sorry, sorry, this cold is just killing me. Okay, the different size stars, right? You're gonna have to explain the evolution of a sun-sized star, like we're finishing today, right? And then the evolution of our larger stars, which will add on to this, right? Everything is the same for the most part up until the point where they leave the main sequence and then things start to change. Okay, so we had our helium flash here. They enter the the red giant branch. They enter the helium flash. They go horizontal in the red giant, and then they even get even bigger. They keep on going up. So helium fusion reaction does not continue long. The helium is consumed very quickly. Okay, what's left in the core is carbon. Sorry, I'm gonna pause this here. Just I gotta get a sip of water and take a cough drop. So I will not be able to talk. Just a moment, please. We'll be right back. Sorry about that. So hydrogen fusion stops, right? Not the hydrogen, helium fusion stops. The helium all gets rapidly consumed, and the helium fuses into carbon. And so you end up with a core of the star being made up of carbon. So nuclear fusion at the core stops. A star this size cannot fuse carbon. It's too small. There's not enough pressure. So fusion in the core ceases. Gravity still compresses the core, right? And because of that compression, it gets hotter and hotter and hotter. This increases the hydrogen burn. Sorry, this increases the hydrogen and helium shell burn. Move me out of the way around the core of the star. So looking at this diagram, we've got our carbon core ash, and then we've got our hydrogen and helium shells. They start burning faster and faster because the carbon core, that carbon ash, compresses and compresses and compresses, gets hotter and hotter and hotter. So the non-burning layers of the star, right? So we got like the radiative layer, the convective layer, the chromosphere, and the photosphere, right? You should have learned all that in grade 10, right? That heat from the shells causes them to expand outward and outward, right? That pressure, sorry, not the heat so much, but more the pressure, right? So that outward pressure from the burning, for the nuclear fusion going on in the shells, causes the outer envelopes, the outer part of the star, to expand and expand and expand. And as it expands, it cools, right? So we go up even higher into, we get even larger, we become a red supergiant. Okay, so the star becomes a red giant, then it becomes a little smaller, and I gotta pause it again. Come on in. Okay, sorry about that. There's lots of interruptions. So the carbon core collapses due to gravity, getting hotter and hotter and hotter. That heats up the hydrogen and helium shells even more. So their fusion continues at a faster rate. Right? So they're giving off more energy, and this energy takes the outer layers of the star that aren't going through nuclear fusion and blows them outwards. So they expand, and as they expand, they cool and they become red. So we hit the red giant phase. So the burning rates are much more intense in the second ascent, this ascent being here, causing the star's luminosity, so it gets brighter, and its radius to increase to an even greater extent. So the star is bigger and brighter. The carbon core grows in mass as more and more carbon is produced in the helium shell. So back here, and let's move me out of the way. The helium shell, right, keeps producing carbon, whereas the hydrogen shell will keep producing helium. So more carbon is produced in the helium shell. So you're getting more carbon, but gravity keeps on shrinking it, keeps on compressing it, getting hotter and hotter and hotter. So it keeps on shrinking due to gravity, driving the hydrogen and helium shells into higher temperatures and becoming brighter. So just to make sure we understand this topic, I've got a question for you. Why does a star get brighter as it runs out of fuel in its core? So the fuel at the core right now has stopped burning. It's all carbon. Carbon can't burn in a star of this size, but the star gets brighter and brighter. Why is that? Because the carbon core is compressed due to gravity. It gets hotter, 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 causes fusion in the shells around the core to increase, right? So they're fusing, like the hydrogen shell is fusing into helium much quicker. The helium shell is fusing carbon much more quickly. So because of that extra rate of fusion, the luminosity of the star increases. It gets brighter, and the star gets bigger. The bigger the star, the bigger its luminosity as well. Move me over here again. So stars with solar masses like our sun, so a star that's comparable to our sun, they never go beyond carbon fusion. Only supermassive stars start fusing heavier elements than carbon. Right? Our star, when it dies, will fuse carbon. There's a possibility of a bit of oxygen, but generally it's carbon where it stops. So stars with solar masses like our sun never get beyond the fusion of carbon. As its core collapses, the temperatures never get hot enough to fuse carbon into heavier elements. Okay, you need a larger star. You need a larger star with a larger core and more gravity for it to compress enough. Right, the more gravity, the more compression for it to compress the core enough to reach that heat that's required. So at this point, the core is no longer fusing anything. Fusion will still happen in the shells, but the star is near its end. So the red giant is now very close to the end of its nuclear burning era. The carbon core density, how dense it is for a meter cubed. So take a meter stick, right? Well, that's probably a lot less than a meter, but take a meter stick and cube it. So a cube that's a meter in each dimension, right? That would weigh 10 to the power 10 kilograms. Okay, so think of a 10, right, with 10 decimal places behind it. Extremely massive. So the carbon core density reaches the point where it becomes degenerate. So what I mean by degenerate is that the electrons get stripped off the atoms, right? And now you essentially have a core of free floating electrons. Think about these electrons. is that the electrons that are now moving around freely, kind of like a soup of electrons, right? The electrons are now repelling each other, right? The electrons, right, they're the same charge. They can't be compressed any further. The gravity's not strong enough to get past the repulsion of the electron, so we can't squeeze it down any further. So the electron pressure, that is the resistance of electrons, like charges repel, does not allow the core to compress any further, and then the core, because it can't compress any further, it can't get any hotter. Right? There's not enough mass to keep compressing. So the core won't get any hotter anymore. It can only start to cool. A small amount of oxygen is formed at the inner edge of the helium burning shell, where we have carbon and helium, and they can be fused, and we get a layer of oxygen being formed as well. One moment, I got to pause it here. Okay, let's resume. So the core cannot collapse any further. The, the repulsion between the electrons of all the atoms only allows it to compress so far. And because it can't be compressed any further, it can't generate any more heat. There's still tons and tons of residual heat. Right? It's still super hot. So the carbon core, so we're now in the stage called the planetary nebula. Right? And this is a planetary nebula. At the center, you can see the core of the star that remains. Right? That's a white dwarf. In the planetary nebula phase, the outer layers of the star that were non-burning, right, they get blown off, right? They drift away. It's not an explosion of the star, right? But they end up drifting away. So these here are outer cores of stars. And all these colors correspond to different elements: hydrogens, heliums, oxygens, and carbons. So the carbon core is no longer generating energy. The outer core shells continue to burn hotter and hotter as the core collapses to its final state, where it's compressed so far it can't go any further, like we mentioned here. It's compressed as far as it can. The outer envelope will continue to expand, okay? And as it expands, the outer envelope will keep cooling and cooling, and it's going to become huge, right? It's going to be 300 times the radius of our sun, right? It will just keep expanding and expanding and expanding. Now, there's some instability still going on, though, in the shells, right? The hydrogen shell here, it'll undergo a bunch of helium flashes due to the tremendous pressure, right? So you have these helium flashes are releases of energy. If you go back to the previous talk, we addressed the helium flashes there, right? You don't really need to worry about the mechanics of it, but we have these explosive releases of energy. So we get multiple helium flashes, and this makes the outer layer of the star pulsate. With each flash, it will get hotter, expand, and then it will cool and contract. Then the next flash, it will get hotter, expand, cool and contract, cool and contract. So these helium flashes will happen, towards the end of the star. And as the core temperature increases because of collapse, right, the amplitude of the pulsations increases, so how strong the pulse becomes. So at the end of a sun-sized star, the star becomes a red giant, and that red giant will pulse. Okay? And we're right near the end here. The star is just about dead. Right? So that core is giving off a ton of radiation, right? And all that pressure from that radiation and other instabilities within the shells, right, will push that envelope of gas, right, the outer layers of the star away. The radiation is so intense. There's so much energy. It pushes the outer non-burning layers away, which gives us here the planetary nebula. A nebula is a cloud of gas, right? So this cloud of gas is emanating from that central point right there. Okay? That is the remains. That is the core of the star. That is what's left behind. That's that carbon core with some oxygen that has been compressed to such a point that I can compress no further. So the carbon core that's left behind, super hot and very luminous because it's so hot, it's giving off heat, light energy. Right? It contracts as far as it can go, and it heats up, and as far as it can go, but it reaches a point where it stops creating new energy. It can only compress so far, and once it's compressed to its limit, it's still giving off heat energy, but it's not creating anymore. It's got residual heat. So that carbon core contracts and heats up, and it gives off radiation, ionizing radiation. So this radiation hits the cloud of gas, and when it hits that cloud of gas, just like electricity traveling through neon gas, it creates light and color. So that ionizing radiation from the core, right, doesn't ignite. Ignite's the wrong word, right? It energizes the ejecting gases to give off light, right? And these colors correspond to hydrogen, helium, right? Some carbon, some oxygen, and so on. What's left behind as that cloud of gas drifts away at the very center is the core of the star, the white dwarf that's left behind. So that star has shrunk to about the size of our planet, but it's got half the mass of our sun. We can fit 1,000,000 Earths in our sun. Our sun is enormous, right? But half the mass of our sun is now compressed into an object the size of our Earth. That object no longer compressing, electron degeneracy prevents further compression. So it's not generating any new heat, but it's still super hot. It's got all that heat from all that compression and all that fusion. So its surface is white hot. So if we follow the HR diagram, right, we had our stars on the main sequence, right, consume their hydrogen, become a red giant, right, come back down, settle, right, start fusing carbon in the core, become a super red giant, right? Planetary nebula gets ejected. Then we have the group of white dwarfs down here. Right? The white dwarfs being very hot, but they tend to be dim because they're so small. And since the white dwarfs are no longer making heat, right, they will start to cool. There's no fusion. There's no more compression due to gravity because it can't compress any further due to electron pressure. So they are going to cool. Right? This cooling will take millions and millions of years, but eventually they'll go from a white dwarf, and as they get cooler, they'll become, yellow and then red. Eventually, they'll cool to the point where they're giving off no light at all, and we have what we call a black dwarf. This black dwarf, mostly carbon and a little bit of oxygen, right? And I've said it here: a cold, dense, burnt-out core of a star. And degenerate electrons, so electron pressure, prevents the core from collapsing any further. Okay, so we'll stop there. I'm going to post this. I'm going to post a note. Right? Make sure you study this. Make sure you understand it. Right? We're going to talk about bigger stars and what happens to them. They don't become white dwarfs or black dwarfs. The bigger stars, eventually collapse into neutron stars, and our largest stars collapse into black holes. And we're going to talk about that. At the end of the week, you're going to have to be able to explain it all to me in a video, very much like I'm doing down there or there. Okay? Have a nice day.